we have most of the pieces, the model, the estimators, information about the distribution of the estimators. We could proceed with inference, but I'm going to put that off for a little while. And what we're going to do now is take a quick detour into something called analysis of variance. And then I'm also going to talk about some sort of practical issues in estimating linear regressions before we get to inference. We'll do inference next time. Okay. So we want some way, typically, to indicate how closely associated x and y are, or how much of y's variation is explained by x's variation. Okay? And what we do is we perform an analysis of variance that I'll do in just a second, and that's going to lead us to a measure of goodness of fit for our linear regression. And that's typically sort of a useful gauge of sort of how the regression is doing in some sense. Okay, so let's start by defining the sum of squared residuals. Okay, so we've actually already seen the sum of squared residuals. That's what we were minimizing, choosing beta naught hat and beta 1 hat to minimize. Okay, let's just define this quantity here as the sum of squared residuals. And here's a picture of it. So the picture can't indicate, each one of these. So what we do is we calculate each one of these, we square it, and we add them together. That's the sum of squared residuals. And this is, in some sense, a measure of goodness of fit, right? But it's not a very useful measure of goodness of fit because it's not unit-free, okay, which is inconvenient. So let's say we have a data set, and both of the variables are measured in, pounds, British pounds, and then we translate both of the variables to dollars. Then the sum of squared residuals will actually change, and that's not a very convenient feature for sort of a measure of fit to have, okay? But if we divide the sum of squared residuals by some other sum of squares, the total sum of squares, for instance, then that gives us a unit-free measure because the units cancel. So what's the total sum of squares? Well, the total sum of squares is we don't even fit a regression line. We just take the sample mean of y and just calculate all of the deviations from the sample mean and square those up. So graphically, what does that look like? So let's say this line is y bar, okay? So what we've done is we've just taken all of the deviations from y bar, squared them, and summed them up. That's the total sum of squares. Okay, so that, so we've got the residual sum of squares and we've got the total sum of squares. And note that that is going to be a unit-free measure of goodness of fit that's always going to be between 0 and 1. Why is it always between 0 and 1? Yep.
Most values are always, so I guess the question is actually, why is the SSR always less than SST? Since they're both positive?
Yeah.
Yeah. Okay.
They're both positive, yes. So you got half of it right. Okay, yep.
Is SST like the maximum error you have?
No, well, no. Yeah, I could draw a line that gave me more error. But basically, you're on the right track. The SSR is the least error you can have. Why is that? That's how we chose the regression line, to minimize that quantity. Okay? So any other line is going to give you higher sum of squared errors. Anything else you do is going to give a higher sum of squared errors than the SSR. Okay? And so that's what, yes, so you got half of it. They're both non-negative by construction, and the fact that the regression line is the least squares line ensures that SSR is always less than or equal to SST.